Hello, welcome everyone. This is part of our bi-weekly tech forums. Today we're going to have a session about RAS handling by Soby, Mathew and Manish, Pandey. I believe Soby is going to start and talk about the generic changes, and Manish will talk a bit more detail about TFA specific changes. So if I can hand over to yourself, Soby.
Hi, hello. I hope I'm audible.
Yep, you're audible.
Okay, so as Joanna mentioned, me and Manish will try to cover the RAS handling topic. So I lead the RMM team and look at RME enablement from an EL3 point of view. So I'll try to explain the generic RAS concepts yeah, Manish will delve into TFA specifics. Yes, Manish, you can move to the next slide. Okay. So I hope everyone is aware of the terminology RAS. RAS refers to reliability, availability, and serviceability. It is referring to hardware errors, as in either errors occurring from within the PE, perhaps cache controllers, memory controllers, or other system nodes. And these errors need to be handled or signaled correctly, and it determines how serviceable and determines the availability of the system. Now, the errors themselves can be signaled via an external abort or IRQ style interrupts. IRQ style in the sense it can be an FIQ as well, but a regular interrupt. The former is referred to as in-band error signal, as in the external abort is referred to as an in-band error signal in the RAS specifications. Now, there are two methods for handling RAS errors, and it's important to have this distinction clarified very well. When we say handling RAS errors, it's always from the non-secure world point of view. So from the non-secure kernel point of view, there are two methods of handling RAS errors. The first one is called firmware first, and the second one is called kernel first. The primary difference here being which entity is responsible for the first level handling of the RAS errors. So if the firmware is handling the first level handler for these RAS errors, it becomes firmware first. And if the non-secure kernel is the primary first level handler, then it becomes kernel first. So I'll explain firmware first in a bit more detail. So in the firmware first handling, the external aborts and error interrupts corresponding to the non-secure world are handled in firmware, and the original RAS exception is not visible to kernel. Okay. The errors are signaled back to the non-secure world, usually via SDI. And in the pure firmware first handling methodology, the kernel is prohibited from accessing the RAS error records directly. The kernel always gets secondary error records called CPR records, which are created by firmware. And then the kernel finds out more about the error through those CPR records created by firmware. So that's the firmware first. Now, kernel first is relatively new compared to firmware first. In the kernel first methodology, the external aborts are routed to kernel, and the error interrupts corresponding to the non-secure nodes are configured as non-secure interrupts. The error records are directly accessed by kernel, and the kernel navigates error records and handles the error as the first level handler. Now, there is a small corner case that an external abort can pend at EL3, even though the system is configured as a kernel first handling mode. And this needs special handling, and we'll discuss more details on that in a later slide. Before I move on to the next slide, is there any question? Because it's important to get this concepts clarified before we move on.
So have we seen any system which has both enabled in it, firmware first and kernel first together?
So both of these methodologies, they are not like binary, as in it is possible to have a hybrid mechanism where it's a mixture of kernel first and firmware first. So I'll discuss some details on the hybrid mechanism in a later slide.
Okay.
Sure. But yeah, from a theoretical point of view, it's usually that system follows one of these methodologies, but then practical implementation means that we need to have a hybrid mechanism some cases. Yeah.
Okay, sure. Okay.
Okay, there are no questions. So this slide describes a typical firmware first handling flow for external aborts originating in non-secure world. So assume that an error happens in the non-secure world, and then because the external aborts are routed to EL3, the external abort EL3 starts executing, and there's a platform handler corresponding to the external abort, which iterates through the error nodes and figures out, okay, this is a RAS error that needs to be handled. And then the platform layer will forward that RAS error to the secure world. And typically there would be a RAS secure partition, which is responsible for further processing that error and creating the CPER records, which is accessible to the non-secure world.
Just one clarification, it's not mandatory to have secure EL2. There are implementation like SPMMM, which directly accesses. I mean, they have their own secure partition to do these things.
Yeah, so this flow is assuming that there's a secure EL2 and the architecture is corresponding to 8.4, any system greater than 8.4, 8.4. Yeah, so the CPR records is created by RAS secure partition, and the control returns back to EL3. And now EL3, the platform RAS handler would invoke an SDI dispatch event, which would dispatch an SDI event back to the non-secure host, signaling the event. And the non-secure host would now look at the CPR record, figure out what type of handling needs to be done, and then calls SDI complete event, which takes the control back to EL3, and then the SDI returns control back to the plat RAS handler. And plat RAS handler now returns back, it returns back to the point of origin where the error happened. So that is the full flow for a typical firmware first handling for an external abort originating in non-secure world. And it's important that this flow is only for the error happening in non-secure world. If the error was corresponding to a RAS error in the secure world, then the flow is completely implementation defined. The error would be contained in the secure world itself, and secure EL2 would have some mechanism of handling it, but this error would never get exposed to the non-secure world. The error is contained within the firmware domain itself. So this flow is only relevant for errors originating in the non-secure world. Okay, is there any question? Okay.
Just one question. In this handling, when you first receive any abort, is that will be masked? Like, will there be reentrancy supported, or it's like is only one abort is being handled? And
so we were executing in the non-secure world, and the external abort happened. So it's just one entry into EL3 at this point in time. Yeah. It is possible that while the EL3 code is executing, EL3 itself can trigger another fault. It's called double fault in RAS terminology. Yeah. So in this scenario is treated as fatal. and EL3 kind of just panics and probably brings down the system, because a double fault is a critical error from which we cannot sensibly recover. Yeah.
Okay, so then that case scenario is handled at present.
Handling in the sense we will EL3 will detect that it has entered a double fault, and it would call a platform specific handler to handle this double fault. And in most cases, the platform specific handler would bring down the system either by informing the BMC or a management entity inside the system, and it would bring down the system after suitable logging. There is no probably there is no continuing of execution after that point.
I mean, yes, it is implemented, and
Okay.
for MVP platform, it just panics.
Okay, thanks. And is that recommended, or it's like necessary to have a RAS specific partition?
So usually we have the partition, which takes care of handling, creating the CPR records. So in the new secure partition architecture, it is recommended that every functionality is contained as a secure partition, yeah, we expect that the partition would run as a secure partition inside under secure EL2.
Okay. No, I mean to ask, like the RAS specific secure partition, will it be doing only RAS specific functionalities, or it can do multiple activities? RAS is one among them.
Yeah, I think that's an implementation choice. So for the purpose of showing this diagram, I showed it as a RAS only secure partition, but I guess the same secure partition can implement other features. Yeah.
Okay. Yeah,
but
thanks.
This is more of what capability the secure world has, and what kind of encapsulation is required for RAS handling. Yeah.
Thanks.
Okay. Now this flow was mainly for external aborts. If there was a interrupt style RAS error happening, then it would be configured as a secure interrupt, and then the secure interrupt would take the execution directly into the secure partition, and the secure partition would create the CPR record, and then the error would get notified via SDI. Yeah. Now, I hinted in the first slide a specific problem related to kernel first handling. So in kernel first handling, there is no such flows involved, because all the errors occurring in kernel side is targeted to the kernel itself. There is no context switch, there is no execution, there is no entry into EL3. But there is a specific case that there's a specific case in kernel first handling that needs to be handled, and this slide is discussing that problem. Assume that the non-secure side makes an SMC call into EL3, and EL3, as part of as part of synchronizing the errors, it issues a error synchronization barrier, and it could be that an error is now pended, but that error is corresponding to the non-secure world. Now, this error is pertaining to the non-secure world, and it needs to be signaled back to the non-secure world. Okay. The ideal solution is for EL3 to inject this as an SRR back to the lower EL. This is typically how secure EL2 signals error back to EL1. And EL2 has architectural support to inject virtual SRRs back to EL1. Now, EL3 does not have this capability. We could have a full SRR emulation at EL3, but it's highly complicated, and it's likely to be error prone, and it would be very fragile, because with every architectural extension, there is some changes with respect to how SRRs are routed, and it would be very fragile. So there is a solution. I call it almost full solution, as in There is a feature in RAS extension called implicit error synchronization barrier. And if the IESB bit is set, it is possible for the external abort to pend at EL3, but not consumed. So if we check the ISR EL1A bit, it would show that an external abort is pending, but it would not be consumed at EL3. And if the external abort is pending, then we can ERET back to the originating lower EL. And if the external abort was unmasked at the lower EL, it would trigger at lower EL, and the lower EL would get a chance to take the exception. And depending on how that exception is handled, it would be a typical SRR handling back in the lower EL. And then it can resume the SMC call back. Yeah, so that's what is being explained in that point over there.
So
there is
just
also-
quick.
Yeah.
Sorry, finish your thought. I'll ask my question after.
Yeah, so that's it works well for the SMC call. SMC calls into EL3. Now, SMC call is not the only way you can enter into EL3. A secure interrupt can also cause an entry into EL3. So if an FIQ causes an entry into EL3, then it is implementation defined whether the FIQ or the SRR is pended first. But there is an architecture recommendation that if the IESB is set, the SRR is pended first at the lower EL, and then the FIQ is taken. So we think that most CPU implementation would do the sensible thing, as in when we do an ERET back to the lower EL on detecting this condition, if both an FIQ and SRR are pending, the SRR would pend first, and then the FIQ would take the control back to EL3. And after the handling of the secure interrupt, on doing an ERET back to the lower EL, you would resume the execution back at the SRR vector in lower EL. And that would take care of the original external abort, and it would correspond to whatever handling kernel had in place for that SRR. And yeah, everything should just work. Yeah. So if there are any questions, yeah.
Yeah, I think it might be a question or comment, right? So, and it's related to pstate.a. So you only have pstate.a on entry, right? And then you unmask it. And I believe that does not cause the SRR to be taken, right?
Yes, because
so it's just accumulated in the register.
Yeah, because the EA is 0, the target exception level for EA is still a lower EL. Okay, so that causes the exceptions to stay pending, but it would not be consumed at EL3. As in, we don't take an SRR exception at EL3. It would show pending. Yeah.
Right. What would happen if EAS, maybe this is an ARM architecture question that I should read the manual, but what happens if EA is set to 1 and you make an SMC and there is an SRR that gets pended just before the SMC?
So in kernel first handling, the EA will be set to 0 because we want the external aborts to be routed back or to be taken by the kernel itself. It's only for the firmware first handling that EA would be set to 1. Okay.
Oh, okay. Yeah, I was definitely thinking about the firmware first handling case, right? In that case, EA would be set to 1. Let's say you make an SMC and there's an SRR pended.
Yeah. So in the firmware first handling, this is not a problem because in the firmware first handling, the firmware is expected to handle the error first. So as part of that handling, it would see that an SRR is when it issues the error synchronization barrier, it would find that there is some error pending, and it would route it to the platform layer, just like we saw in the previous slide. And the platform layer would route it to a corresponding RAS partition, and then it would get signaled back to the kernel through SDI. So all of that flow would just would take care of this case. This problem is only for kernel first handling because in kernel first handling, the kernel is not expecting an SDI event to, it is not expecting to be notified by SDI event. It expects to handle the error by itself. and hence this error needs to be reflected back to the lower real.
Okay, yeah, makes sense. And in both cases, the pstate.a can be essentially aborts can be unmasked, right, after entry into EL3 and synchronization of S error.
In the specific sequence for firmware first handling is we do ESB with aborts masked, and that would cause the error to reflect in DISR EL1 register. And then you unmask the external abort at EL3. That's the sequence for firmware first handling.
Okay,
yeah, but
and that wouldn't trigger an S error in EL3.
Yeah, else it would trigger a S error at EL3. If it were masked earlier than the synchronization barrier, it would trigger an S error at EL3. Yes.
Okay, thanks.
Okay, so this has maybe we can go to the next slide. So this slide compares KFH. Some benefits of KFH is because kernel is getting to handle the error itself, there is no cycle stealing from non-secure world. So this is a concern for mainly for cloud vendors, because the errors can cause cycles to be basically the secure world will need to handle the errors, and hence the kernel has no visibility on what is happening, or it loses control of execution. In kernel first, everything happens in non-secure world itself, and hence everything is visible to kernel. And in kernel first, there is less possibility for recoverable RAS errors panicking the system because of firmware issues. Okay, if there was an improper firmware, or there are some firmware integration issues, because kernel is handling the error itself, it as long as it has the right handling, it can recover from recoverable RAS errors. There is less context switch involved in the whole flow, because as you saw in the previous slide, firmware first involves switching between EL3 secure and non-secure in a series of sequences as part of the handling. There are some disadvantages now, because the kernel first handling, we need the kernel support. It is likely that the mainline kernels will only support standard error record formats, which means that if there is a system IP or a system error record which is not the standard format, the upstream kernel is not going to have the corresponding driver for handling that error, handling that format. And hence, for kernel first handling, one of the requirement is all nodes need to implement the error records in the standard format, whatever is supported by the kernel. Because firmware is less involved in kernel first handling, there is less possibility to notify the firmware domain errors back to kernel. Usually, kernel may want to keep track of all the errors in the system just for maintenance purposes, to find whether there is a failing peripheral or not. And in kernel first handling, because the firmware domain errors are contained within the firmware and it's not signaled back to the kernel, we might need some implementation defined solutions to do this. And there are some more restrictions on the kernel first handling, as in the kernel needs, in kernel first handling, if there is a shared entity like a DDR controller between two worlds, it must there are some system level requirements, as in the kernel must not be able to mask error generations related to secure world execution, and hence there is more restriction in the overall system level, and that could be a disadvantage for implementing kernel first handling. So hence, I think there is a recognition that it may not be possible to implement a pure kernel first handling, at least initially. And we think that it should be possible to have a hybrid mechanism where, yeah, it's possible to have a mix of both firmware first and kernel first. And this shows a spectrum between kernel first and firmware first. So essentially, in the leftmost box, it shows the pure kernel first, where all the external aborts are routed to kernel. All the non-secure error interrupts are configured as non-secure IRQs, and all the error nodes are accessible by kernel, and they are all in the standard format. And the next box shows a slight variation of that, where the external aborts are routed to kernel, but some error interrupts are handled by kernel, but others are routed to firmware. The ones routed to firmware would need CPR records created by the firmware. So there is a possibility that some error interrupts are configured as secure interrupts, and then the secure world gets to handle them first. And the secure world creates CPR records for that. And the kernel is notified correspondingly. And yeah, the kernel handles them as a second level handler. The box next to that is a further variation where the external aborts are still routed to kernel, but all error interrupts are configured as secure interrupts and are routed to firmware. And hence, any error records created due to these error interrupts are all CPR records. And the kernel needs to be able to access these CPR records and handle them as a second level handling. And the rightmost box is the pure firmware first handling, where everything, external aborts and error interrupts, are routed to firmware. And everything is, all the errors are created as CPR records, and the kernel needs to access CPR records to figure out what error happened. Okay. Now, so till now, we were mainly discussing a traditional two-world system where there is a non-secure world and a secure world. Now, with the introduction of RME, we have another world, realm world, and we need to extend this concept to the realm world. Now, realms are considered as confidential virtual machines, and they are considered an extension of or counterparts of virtual machines existing in the non-secure world, but they are confidential. And hence, the RAS errors occurring in these realm virtual machines, they are pertaining to the non-secure host. Now, RMM, which is the manager component in realm world, that is still considered part of the firmware domain. And hence, any errors within the RMM are meant to be handled within the firmware domain. Now, depending on where the realm errors are routed first, we can extend the kernel first and firmware first handling methods to the realm world as well. So if the errors occurring in realm world are handled first by the kernel directly, then it becomes kernel first handling as far as the realms are concerned. But if the errors occurring to the realm VMs are handled in firmware domain and correspondingly in a secure partition, then it would be considered as firmware first handling for the realms. Yeah. So this flow is showing the kernel first handling in case we were to apply kernel first handling in a 4-world system. Manish, if you can click the side. So if an error in kernel first handling, if an error happens in non-secure host, the non-secure host handles it. In case of secure world, the errors are meant to be handled within the secure world, irrespective of firmware first or kernel first. The secure world gets to handle its own errors. So any errors occurring in secure partition, it's a private matter between Hafnium, secure EL2, and secure partition, how that error gets handled. Now, if an error happens in realm world, it gets routed to RMM first, and then RMM would, Manish, if you click next, RMM would transfer control back to EL3, and then EL3 would, yeah, Manish, next. my EL3 would transfer the control back to non-secure host. And in the kernel first handling, as I mentioned earlier, any error happening in the realm, if the non-secure host is the first entity handling that error, then yeah, it becomes kernel first handling. Okay.
Hey, so quick question on that. So you're saying that in your last slide, you said RMM spec naturally allows for this, right? Is it just that anytime there's any sort of exception, it just an interrupt, you exit realm world and you go back to non-secure?
Yes.
Okay.
Yeah. So any exception happening in realm world, we return control back to the non-secure host. So in that way, RAS exceptions are not special. It's just like any other error happening in realm, and we just return back to the non-secure host, and the non-secure host inspect the error syndrome and does the appropriate action. So kernel first handling kind of fits nicely with how we do RMM and realm world today.
And is that an implementation choice or a spec choice? Sorry.
So the RMM spec mandates how the errors are to be returned back to non-secure host. So given that the spec is catering for this errors, errors happening in realm world being, returned back to non-secure host, the spec kind of naturally facilitates kernel first handling easily for realms. There is a backup slide which shows how we could possibly do a firmware first handling. But yeah, I'll not be covering this as part of the presentation here. Yeah.
I have a question. On the clarification is like when we handle a CPU error, why you see it's a non-secure word error, secure word error, or RAM error? It's a CPU error, right?
Right. So depending on the software context at which the CPU error happens.
The CPU error is the hardware trigger signal.
Right.
Yeah. So depends on where your error handler is located. So if that maybe the secure word, if it's firmware first, the secure word should pick up the error handle. It doesn't matter. It's like when you have a program is running in secure world or normal world, it's a CPU error. So it depends on where you put the error handler, then it should, right?
So in RAS, there are, errors are broadly categorized into corrected errors and uncorrected errors. Okay. Now in uncorrected errors, there are further categories. There are 4 categories: recoverable. Sorry. There are 4 categories: restartable, recoverable, unrecoverable,
uncontainable,
unrecoverable, and uncontained. Okay. Now restartable and recoverable, it is possible for software to, as long as the proper handling is done, there are ways to recover the system, as in we don't need to panic and bring down the whole system. Now,
So my understanding is, software is a lot of the time is just do the recording. The error happened, and then the hardware is handling all the error recovery. Or sometimes of course software, but a lot of time is a hardware. So the error handling pretty much is provide a log of what the history of what error has happened.
Yes, there is a history, and there is also the case that assume that the CPU error happened, a recoverable CPU error happened while execution of a user space program. Okay, and if it is user space program and the system is still recoverable, it is possible for the kernel to kill that specific user space process, but still retain the rest of the system. So hence the context in which the software context in which the error happened is important for the recovery of the system. If the system is always going to panic, then the software context is not relevant. But if recovery needs to be done, then the software context becomes important.
Yeah, you will retry the software. And
Yes.
then I have another clarification I want you to explain to me is firmware first and the kernel first. So my understanding, firmware first is you handle the error in the firmware first, and then you still handle it. If it is necessary, you can also let the kernel handle the error, right?
Yes. Yeah, so in firmware first, the first level handling happens in firmware, and which is usually just taking the interrupt and creating some error records for kernel to do the second level handling. So that's what happens. Whereas in kernel first, the kernel handles the error directly, and it's only the kernel which gets involved in the whole process.
So this both KFH or FFH notion is for component which is doing the first level handling. So if it is done by firmware, then firmware first handling, otherwise kernel first.
Yeah, so if it's kernel first, then firmware basically will not do anything, right?
Yes.
Yeah, so when we say kernel first and firmware first, we have to remember that we are talking from the non-secure point of view. So these are errors happening due to non-secure world. Okay, firmware first and kernel first does not affect how errors are handled for errors happening inside a secure partition, for example. So if an error happens while execution of secure partition, then it's up to the secure partition manager how to handle that error. It will not be exposed to kernel. So this two methodology is only talking about errors happening while executing non-secure software. And when we have realm world, it also extends to realm VMs. Okay. All right, I'll hand over to Manish for.
Thank you, Soby. Can you hear me all right? I'll be covering the second part of it, which is TFA implementation related with what we discussed so far. And it includes the existing code base and what improvement has been done as part of this refactoring. So I'll start with the EL3 exception handling. So for vector entries which are from current EL, as in the EL3, the errors exceptions caused by EL3 itself, there used to be a special handling for the issue, the KFH problem we discussed earlier, but now we don't need it. So it does not need any special attention if the exception happened in current EL, as in EL3. Or exception arising from lower EL, if it is synchronous or hierarchy interrupt, we need to. So what we need to do is, even before handling the original exception, we need to check for any external aborts which were caused because of synchronization barriers, and then we will distinguish whether it is firmware first. In case of firmware first, it's firmware's responsibility to handle any EA arising from lower EL. So it is anyways passed on to the platform handler in case of FFH. And in case of KFH, to solve the problem we discussed earlier, we need to reflect the external aborts to lower EL. But there is a special handling also therein. We need to take care of we need to take care if the EA is masked in lower EL. So what will happen is, say we make a SMC call, we come back to EL3. In EL3, we saw a pending lower EL EA, pending EA. We go back to lower EL and it is still masked there. So that will not be handled and it will come back to EL3 again. And this will be a to and fro between lower EL and EL3. So to break from that errorness scenario, we just have had a workaround wherein we just keep track of the previous link register into EL3 and the number of counts, how many times that ELR has been there in the history. And if it reaches a maximum number, currently it is fixed as 100, then we just do panic. So once we either invoke, once we are done with the EAs caused by synchronization barriers, we go back and handle the original exception. For S errors, in firmware first handling, it's straightforward. You just invoke the platform handler to do the handling. And in KFH, we never expect an S error from lower EL into EL3 if we have set up KFH. So I will go through the macros which are related with or are directly doing the RAS related things in TFA. So, so the current TFA code base has a RAS extension build macro, which is now with the new patches, we are going to get away from this. So earlier in TFA point of view, the RAS extension meant only FFH. So there was no support for KFH, even if it was the system would have the KFH support, but it was firmware is unaware of any RAS related things. So the first macro is enable fit RAS. So recently we have started with a feature detection mechanism wherein we put all the features as fit underscore something, and we to bring it in line with other features, we renamed it to enable fit RAS. And what it will provide is just ESB instruction for synchronization. So for FFH, it has to be 1, and for KFH, which is the default configuration, it can be 0 or 1. The firmware first handling, we have introduced a new build macro for firmware first handling, and it is 1 for FFH, 0 for KFH. The EL3 exception handling, this macro is already there in TFA codebase, and this is basically to use TFA exception handling framework. This is used to register any handlers, for example, for SDEI or any other handlers for prioritizing the exceptions. Handle EL3 first non-secure. This macro is for basically routing external aborts to EL3 if it's happening in lower EL. This basically sets up the EA bit. So for FFH, we must have it enabled. For KFH, it will be 0. Again, the new macro which has been introduced is allowing lower ELs or allowing non-secure vault to access error records. So as we discussed, like in pure FFH, kernel is not allowed to access any records, and in KF, so it has to be 0. But there may be a scenario wherein even especially for the hybrid mode, wherein even though it is FFH, kernel may need to access some of the registers. So to support that, this macro has been introduced. SDI support, this is the backend of notifying back to non-secure vault. It has been there. And for FFH, there could be a different mechanism to report it back to non-secure, but currently we use SDI. And finally, this fault injection support, this has been introduced in 8.4 architecture. This gives lower ELs a capability to inject fault. And we are using this macro just for testing on FVP. It is not mandatory to use the RAS extension feature. So the existing RAS extension, so the changes which are there in the review now, which I'll talk about later on. So the existing RAS extension is now equivalent to enable fit RAS and FFH support. So the platforms which are using RAS extension now need to change this into enable fit RAS and FFH support. For existing platform which are upstream, I have already done it, but for downstream platform, this change has to be done. So patches under review, they are under the topic fit RAS. What it does is replacing existing RAS extension build macro with fit RAS, providing support for hybrid mode of RAS handling. So basically allow error record access implementation, reflecting SRR to lower ELs. So this is to fix the problem we discussed for KFH case. This also refactors and unifies some of the functions which were used in lower EL SRR vector entry path. And finally, the documentation. So documentation, whatever we are discussing here now, and along with that, more details we'll be updating in the TFA documentation. And also in the past, there were a few patches merged. I wanted to highlight these because one of them was especially a bit risky on LTS branch. So it was merged and then reverted back. So that patch, that change was to allow SRRs during EL3 execution. So I'll give a bit of context. So current, the TFA, the SCR-EL3 is per world. So we keep a copy of SCR-EL3 for individual worlds, non-secure, secure, and realm. But EL3 itself, for its own execution, does not have its own copy. And this value is basically whatever. So whenever you come to EL3, the SCR-EL3 will be same as what which world you have came from. So if you're coming back from non-secure world, it will have different value in EL3 execution. If you're coming from secure, it would have different value. And this was causing an issue wherein, say, when you enter EL3, the SRRs were, external aborts were masked. And when you enter, when you iterate to lower EL, and once, if that world has unmasked the external aborts, so SRR caused by EL3 will be generated in lower EL. So this was the issue, which was fixed by allowing SRRs during EL3 execution. Removing the saving of SCR EL3 during EL3 entry. So we were saving the SCR EL3 value in the memory whenever we enter EL3, but since we do not, lower ELs do not have access to change this register, and we in EL3, there is already a copy of it. It's not required to save and restore on each entry to EL3, and some minor fixes and refactoring done. So few of the functions like handle async EA and inter lower EL async EA, there are quite a few of these functions to confuse, and they basically doing almost same with the different functions. So the refactoring was done to clear up the exception entry path in EL3.
Sorry, can you explain that allow SRRs during EL3 again? I thought that was always the case, right? I believe in all paths we do unmask SRRs during EL3 execution.
We were not doing it. So what was happening is, at boot time, we set up SCR EL3 nicely, allowing SRRs. And once you go back to non-secure and come back, and let's say the non-secure world has EA bit 0, meaning it will do kernel first handling, right? So when you context switch from non-secure to EL3, the value will be still there, because we do not have a copy of SCR EL3 for root world execution. So the value is similar to what is there when you were restoring for the given world. So if once you enter EL3, you restore non-secure world's SCR EL3 copy, and there if the EA bit is 0, it means for duration of EL3 execution, it will be masked. SRRs will be masked.
So Raghu, in order for error to trigger, external aborts to trigger, there are two conditions which must be satisfied. Okay, the first condition is P state A bit should be unmasked. Okay, that is the first condition. The second condition is the target exception level of EA should be EL3. Again, that is controlled by SCR EL3.EA bit. Now, if EAs were not routed to EL3, what was happening was EA's SCR EL3.EA was 0. And during the execution of EL3, EL3 itself triggered an external abort. It never pens at EL3 because SCR EL3.EA is 0. And when you ear it back to the lower EL, depending on the target exception level of that external abort, it pens over there. Now the lower EL has no idea what this error is about because this error was originally caused by EL3 execution itself. So it is essential as part of executing EL3 firmware, it is essential in addition to unmasking the A bit, it's also essential to target the external aborts to EL3. And that is what is being done by changing the SCR EL3 EA to 1 every time, irrespective of whether the EA were routed to EL3 or not.
Oh, that's an architectural issue? Oh,
yeah, so
or that's the behavior of.
That's the behavior of.
Odd.
Yeah.
No.
EAs
I would have expected
yeah.
I would have expected that you set pstate.a to 0, and then if an S error is caused by EL3, it would trigger E-rate is context synchronizing, right? I would have expected the S errors to show up.
Yeah, it doesn't because
the SCR EL3 has a unique behavior. So if it is non-EL3 and the value is 1, it means everything will be targeted to EL3. But if the execution is at EL3 and if the value is 0, or if the value is 1, it will again come to EL3, and but if it is 0, it will never end.
Yeah, so the target exception level of the external abort is important. And that is determined by a couple of bits. So you have some HCR control, which determines whether the target exception level is EL2. And then you have this SCR EL3.EA, which is kind of a superset of that. So if SCR EL3.EA is set, that means the target exception level is EL3 for all S errors happening in the system, regardless of which EL you are executing at. So if that EA bit is 0, then it falls back to whatever setting is done at HCR EL2. And depending on that, the external abort will pend at that target exception level. So it's kind of a corner case, I guess, which is not easily understood.
Now, so this is kind of a solution which will be there until we. So currently we are also in process of creating a root context apart from the individual world context. So once we are done with the root context, we specifically no need to go and change the EA bit. Otherwise, rather we will just restore SCR EL3 while entering into EL3.
Yeah.
So the tests as part of this implementation. So there was a few tests earlier, but we to cover all the paths, there are few new tests has been introduced in TFTF. So there are 3 scenarios. One is you route EAs to EL3, but there is no RAS extension in the system. So to test that scenario from TFTF, just cause an S error and ensure that it traps into EL3, and same for synchronous EAs. For kernel first handling, we do register RAS error handler just to make the test go through and inject an S error in TFTF, ensure that TFTF S error handler has been called. So it's a straightforward, there is no firmware involvement in it. The second one is test RAS KFH ESB because of synchronization. So this will test the problem we discussed about KFH, wherein we have to, the EL3 has to reflect the EAs to lower EL if they arise because of synchronization barriers. And for FFH, this test was already there earlier, wherein you register an SDI event, inject a non-recoverable error, it traps into EL3, and we get notified back to a non-secure through SDI. There is a typo. And for similar to that, there was an uncontainable test, which injects a non-containable error. And considering FVP does not have handler for this, it just panics. So for now, we are just using FVP platform for testing, and any platforms, real platforms, if people are using and they do have the RAS tests internally, we would request to have some feedback on the patches, because many implementations or many changes in here, they are very much corner cases, or they cannot be reliably tested on FVP. So we are doing as much as we can, or as much as FVP supports, but having a feedback from real hardware is really good. Ongoing work. So there is a major work currently ongoing in TFA about feature detection mechanism. I wanted to highlight this thing is so far in TFA, it's mostly static. As a platform integrator, you have to decide what all features you need while creating the platform. So the feature detection mechanism is now making it a bit dynamic, wherein you go and read ID register for a given feature, and if that feature is supported by hardware, it will be automatically there. You don't need to enable or don't need to add any special build macros in your platform makefile. So the feature detection currently provides 3 set of configurations. The first one is if you are sure that the feature is going to be disabled in for your platform, then the dynamic check will never happen. If you are sure that the feature is going to be there, then you can set the value to 1, and in that case also the dynamic detection won't be happening. But if you are unsure about a feature and let the hardware decide it, you can set the value to state 2, and in that case, every time you do context management switch, you read the hardware ID registers and do the save and restore or for that feature. So then the planned work is to make RAS extension also go through the feature detection, and the default implementation will be kernel first handling. So if a platform, if it does not provide anything in platform makefile about RAS, it will by default kernel first handling. Fit IESB, it was discussed earlier that about one of the in the kernel first handling problem about Fit IESB. It is a different extension than RAS, and it introduces a support wherein whenever you do a context switch, there will be implicit synchronization barriers. We recommend from TFA point of view that if RAS is supported, the ISB is also assume that it will be there in the hardware. So the implementation we are planning to do is for all RAS, if the platform supports RAS, we assume that ISB is also there. This can be a bit controversial. Not sure if there are any implementation wherein ISB is not there, even though the RAS is there. Also, there are quite a few build macros in TFA to handle RAS. What we'll explore if we can reduce the number of flags and enable them silently if FFH support is there. there is extra test which we plan to introduce is to do the full-fledged FFH flow, wherein we involve secure partitions and to collect the errors and then notify through SDI. So the second bit is already there in our test TFTF repository. The first one is not there, even though a few platforms do support SPM doing the SEPA records. So we will try to include it in TFTF as well. And so for the KFH problem, there is so from architecture, it is not guaranteed whether SRR will pend first or IRQ, FIQ will pend first. And this is causing this is implementation defined. So once we support IESB, fit IESB, and that in that case, it will be we can add the test for these two as well. And finally, we need to ensure that all the possible exception handling paths are covered in testing. So all the paths we need to make sure that are exercised in the testing coverage. Any question? So that is it from us. Any questions?
Manish, can you hear me?
One question from my end. So you mentioned that. Hello.
Yes, go on.
Yeah. So you mentioned that the errors which occur on the secure world should be contained only in the secure side, or similar to the errors which occur in let's say at EL3 should be contained within that. So let's say we have configured errors to be handled as in the kernel first way, which means we have programmed interrupts to be group 1 non-secure. And let's say a CPU error occurs, and that is that when a P is executing in a secure world, there is a error that occurs. So even in that case, the error would be taken to the kernel, right? So how would we contain that within secure world in that case?
Yeah. So that's a good question. So as part of SPSA, there is a recommendation that uncorrected errors for these kind of nodes like CPU, cache controllers, memory controllers should be in-band errors, as in it should be signaled via external aborts SRRs, which means that it is possible to isolate it to that particular world. If it is coming as an interrupt, then probably kernel first handling mode cannot be applied to your system. That's one of the limitation of kernel first. You have to revert to firmware first handling. So we would expect that if you want to do kernel first handling, then such errors are signaled as in-band errors, as in S errors.
And handled in EL3 only. Okay.
Not necessarily. So if it is in-band errors, it means that error synchronization barriers at EL3. So if the error happened in secure world, it's an external abort. External aborts gets picked up by Hafnium, and then Hafnium can handle it. It is no longer an interrupt anymore.
Yeah. Okay.
Yeah.
Good. Thanks.
So there is a backup slide which shows some system level requirements. Manish, if you can go back, yeah. So there are some assumptions for RAS handling, and it mentions some of these, system level requirements, and some of these requirements are quite strong for kernel first handling compared to firmware first. Yeah, so that's why we think it must be, we need to have a hybrid capability for some time till lot of capability and a lot of the system peripherals can implement some of these requirements needed for kernel first handling.
Any final questions for Soby and Manish? We've overrun a little bit, unfortunately. I'm not hearing any, so I'll be making the recording and the slides available on the TFA Tech Forums page in the next day or two. And if there's nothing else anyone needs to say, I'll sign off and thank you all for attending today.
Thank you.
Thanks.